So next up for the transition metals topic then is to have a look at some specific examples of sort of cases being made for the fact that transition metals have variable oxidation states. That's a fact, they do. We're going to look at a few sort of interesting examples of it basically. Then that'll take us into the following lesson where we'll look specifically at redox titrations, which inevitably from the name involves a change in oxidation state. Before that, there's one thing I felt I should add in from a previous video. So if you've been watching this video series in order, then a couple of lessons ago when we looked at the fact that these metal ions form complexes, I glossed over quite heavily at the end of the video carbon monoxide poisoning. I thought I'd better go back and just acknowledge that and cover it slightly more thoroughly. There's very little to say. So here we are again, just for 2 minutes or so, looking at heme. There we've got oxyhemoglobin, that structure there on the right, because you've got well, it's heme. That's iron with the porphyrin ring around it. You've got the globin bit, which is the protein, which is forming its coordinate bond from underneath there with that histidine side group, and it's oxyhemoglobin because there you've got the oxygen. Now we heard it was on the spec about carbon monoxide poisoning. There's the structure of CO. It's a funny structure. We're not going to think about this too hard at A level. There's no reason why we can't handle it, but we'll stick to what we need to know. I hate to say that, but definitely sensible in this massive topic. A good way of thinking about carbon monoxide structure would be something like that. Let's not think now about charges and such. That's fine. Now, CO has got a lone pair. It's actually got two lone pairs. It's actually the carbon lone pair rather than the oxygen one in this case, which would form the coordinate bond with the metal center. And actually, that bond would be quite strong. So carbon monoxide forms coordinate bonds with iron 2 in hemoglobin, or in hemoglobin, just like oxygen, and just like some CO2 does as well. But not all CO2 is transported by hemoglobin actually, but it does happen. Thing is, that bond between CO ligand and iron in hemoglobin is actually quite strong, and oxygen has quite a difficult time displacing it. So the way to treat carbon monoxide poisoning is to basically give the person lots and lots of oxygen to increase the concentration of O2 in the blood, in the system, basically around the hemoglobin that's been had the carboxylate group added to it, the CO. And basically ligand displacement will happen very, very slowly. But as you've seen here, basically CO forms a stronger bond, coordinate bond. It acts as a ligand with iron than oxygen does, iron 2, sorry, in hemoglobin. So basically it gets in the way, it blocks the site that oxygen would bind in, and so you can have a lung full of oxygen and very little of it actually get into your tissues through oxygen transport because of the fact that the hemoglobin can't carry it because CO is getting in the way. That's all there is to say. However, I'm always going to add a little bit more. So, final slide on this little addition. Cyanide poisoning works in a similar way, actually. Cyanide, we're more familiar with its structure from all the organic chemistry, where we've handled it as a nucleophile. And there it is. Again, it's the lone pair on the C, interestingly, which forms the strong coordinate bond with the metal center, similar to carbon monoxide poisoning. That'd have to be something cyanide. It's going to be an ionic substance, so sodium cyanide, for example, or hydrogen cyanide, HCN. But there we are. So that's how poisoning of anything hemoglobin related works. The poison, the toxin, so that'll be CO or perhaps cyanide, acts as a ligand, but it forms a stronger coordinate bond to the one that oxygen forms, and so blocks access basically for oxygen on hemoglobin. Anyway, I'm glad I wanted to clear that up because I felt that it was glossed over when I did that lesson. So, onto the actual new content for today that belongs under this heading, and that's variable oxidation states. We're going to flick through 2 or 3 examples basically of transition metals exhibiting their variable oxidation states. That's pretty well all we're doing. So hopefully it's more notes, but hopefully this is not too bad. So out of interest, let's have a look at this set of diagrams here. The one on the left you should recognize if you've been following this video series, which you will have been if you're in my class, because there you are, there is the electronic structures. We worked those out. We paid special attention to chromium and copper because there was something to be said about their electronic configurations being a bit different. Anyway, it relates to their electronic structure, obviously, because we're talking about oxidation states, which is all about numbers of electrons coming or going, really, when you change oxidation state. But there's a pretty smart, neat pattern there, isn't there? Manganese, okay, 5 unpaired electrons in 3D, can have quite a few oxidation states. Not all of them are stable, okay? So we don't see much manganese 2. Oh, sorry, yes we do. We don't see very much manganese 1 or manganese 5 perhaps, but manganese is a very versatile element in terms of redox. We barely ever see iron 1 or copper 3, though in theory they could happen, and so forth. Scandium and zinc aren't transition metals because they don't form ions which have a partially filled d subshell, remember. Anyway, there's a lot of variety basically in the transition metal block when it comes to what oxidation state the species can have, and those in the middle of the D block in particular have got the most sort of flexibility with what oxidation states they can occupy, or they can have, sorry. Just for interest, so we won't hang around on this one for too long, there's basically the same diagram showing some slightly different sort of categorizations of what's uncommon and what isn't. But there it is in a different form, and there you've also got 4D and 5D, just for interest. So yeah, they can have variable oxidation states as we were aware from the beginning, but it's worth noting how many oxidation states some of these elements can actually have. So first installment in this sort of, like I said, list of things to think about, sort of little nuggets of fact. So first of all, we'll pay attention to these E values. By all means, as many times as you need to when you're watching this, pause the video if you need more time. What patterns do you notice there? I'm going to just immediately talk straight through it, so pause if you want more time. Well, when I look at that, I think, crikey, that's complicated, and it makes my eyes swim a little bit. Maybe I should have changed the text colour, but hey-ho. Seriously though, well, they're all written as reductions. These are electrode potentials, as you can see with the E values written as reductions there. More specifically, they're all iron 3 being reduced to iron 2 as we read left to right, and therefore iron 2 going up to iron 3 if we read it right to left. Evidently, those 3 iron species that are getting reduced, so those 3 iron 3 species, are all different from each other. Let's just focus on the top 2 because I think these are the most comparable, because there we've both got a hexa ligand complex, so a hexaqua or hexacyano, iron 3. They have different electrode potentials despite being iron 3 hexa something or other going to iron 2 hexa something or other. So in terms of the geometry, they're the same. In terms of which metal it is, they're the same. Obviously the ligands are different here. The oxidation states are the same. It's 3 to 2 and back again, and so forth. And same down there. Clearly it's quite a lot different from the others. We've got here some kind of solid ionic lattice rather than a small, simple, complex ion, which would have a negative charge to match. But yeah, they all involve that reduction. So really the point we're going to take from this is that as well as things like colour being affected by ligands and such, actually electrode potential, i.e. redox potential, how good a reducing or oxidizing agent the species is, that's also affected by what ligands there are. So when we talked about colour, we said that there are a series of variables that will affect the colour. So for example, we said different ligands will affect the colour because that affects the splitting and the d orbitals and therefore the wavelength of the photon that would be absorbed, and so on and so on. For that same sort of reason, right, we're thinking about electron energies there. The availability or the ability to accept electrons in when you're doing oxidation or reduction, that will also be affected by by the ligands. So the long and short of it is, and I've really beat around the bush a bit here, you get different E values, i.e. the redox potential is affected by the ligands. Fine. Let's have a look at another series of examples then. So we're going to just say the same thing here, but let's just consider it as well as we can. First of all, let's compare these halide ligand complexes, so chloro, bromo, and iodo. You don't very often see iodide, they're acting as a ligand, by the way. It's far too big to be fitting around a 3D ion, for example. But when you get into sort of bigger ion territory with different orbitals available, you do. Anyway, similar to this first set of examples, these are all gold being reduced to elemental gold. What's the oxidation state of Au in these tetrachloro, bromo, and iodo complexes? Well, it's oxidation state +3. We've got 4 negative ions, which means the ion must be 3+, because the overall charge of the complex ion is 1-. Again, you can see that having different ligands has affected the ability for, here gold, tetrachloro gold or tetrabromo gold to act as a reducing agent or an oxidizing agent. So yeah, you can see that has an impact. We've got this tetra aqua here. That's interesting just to observe, just taking it as an example, but we'd expect normally water to form a hex aqua complex. Here it's got a tetra aqua complex. We're not going to dwell on that. But again, it's gold 3 going down to elemental gold 0. It's a much better oxidizing agent than that one, okay, because look at the values as a comparison. Now, so that's all there is to say there, really. It's just to observe that, since we're familiar with electrode potential being a numerical indication of how good an oxidizing agent the species on the left is, or how good a reducing agent the species on the right is, the fact that they're different, despite all being gold 3 to gold 0, tells us that it must be the ligands that are having that effect. So acknowledge that. Now, a little bit more on the same sort of line, but maybe we'll say something different here. Those equations are really quite complicated to look at, so take your time by all means. There's some awkward balancing in there as well with the halves in the second equation. We're going to play the same game as what we've already done twice now with this element, with chromium. Here we've got chromium 6 in both cases, being reduced down to chromium 3. We'll worry about what's going on here with the hydroxy ligands and the aqua ligands when we look at the final installment in this topic. We're going to look at that in it. But basically here we've got chromium 6 going down to chromium 3 in both cases. Oh look, and what a surprise. As we've seen for the other two elements, for iron and gold's examples, the electrode potential is different. So dichromate appears in this as an oxidizing agent in this second equation. Dichromate in acidic conditions is a much better oxidizing agent than chromate, we call that, in alkaline conditions. Now, you might be wondering, why are these formulae different in the first place? And I think it's best if I just tell you. It used to be on the spec years ago. It's not anymore. Used to have to cover this in detail. But when you put dichromate into alkaline conditions, it turns into chromate. And if you put chromate, which is the one on the top there, into acidic conditions, it turns into dichromate. It's an acid-base type reaction. They're both chromium 6. Anyway, the fact that they're different is really the point that we've made here. Since we're talking about pH, because we're talking about acidity and alkalinity, that takes us to another point, which is to say that as well as ligands being different, the acidity of the surroundings will affect the sort of pH profile, will affect the redox potential. So those two chromium 6 species don't have the same oxidizing power because of the conditions, basically. If I were to take this chromate species at the top here from alkaline and put it into acidic, so if I poured a load of sulfuric acid into it, it would turn into this, and then this equation would be relevant, and then I'd be talking about a much better oxidizing agent. So in conclusion then, and I'll also say this, now backtracking for a minute, there'd be another equation that these would be coupled with, so you'd have dichromate oxidizing something else, for example some zinc being oxidized up to zinc 2 or whatever it might be. We always consider these reactions to be reversible, and so even though temperature is the only variable that actually affects Kc, you always get shifts in equilibrium when we change concentration. So if I poured a load of extra acid into this, I'd shift the equilibrium to the right, and that would affect the electrode potential. Anyway, the point to be made really here, after we've said what we had previously with gold and iron about ligands making a difference to the electrode potential, and therefore what we mean really is the reducing and oxidizing power, is to say that pH also has an effect, full stop. So if you need to take any notes, then just pause quickly. I appreciate this little nugget of the course here is pretty obscure, and the examples that we have to work with are usually not very easy to access. Like those equations are quite tricky to get your head around. So moving on to vanadium. So we're kind of shifting our focus now. Chapter 2 of this lesson, vanadium. Now, we've got a load of colours to learn for other metal ion species at the end of the course. It's the last thing that we'll be doing if you're in my class. However, you need to know these colours too. It's not too bad, however, be aware of them. So, vanadium. Now, let's work out the oxidation states of the vanadium in the yellow and blue. We can easily see that that's vanadium 3 and that's vanadium 2 for the green and the violet. But what's the oxidation state of V in VO2 plus? As opposed to the oxidation state of V in VO2 plus. You can see that they're both VO2 plus. It's just about how you make sure you know which one you're talking about. Well, the one on the left, I can see it's got an overall positive charge, 2 oxygens. We'd assume their oxidation state -2, so that must be vanadium 5. And here, following that same sort of logic, overall charge +2, -2 oxidation state on the oxygen, which means the vanadium must be +4. +4 -2 gives us the overall charge of +2. Now, A bit more electrode potentials to play with, just to sort of make a point here about successive oxidations or reductions, well, redox reactions. So we've got our vanadium 5 species here, written as a reduction, going down to the vanadium 4 species. That's the yellow to the blue, VO2 plus to VO2 plus. Then that VO2 plus, vanadium 4, could be reduced further, given the right conditions, down to vanadium 3. And then again, given the right conditions, the vanadium 3 can reduce all the way down to vanadium 2. And some reducing agents will have the power to take VO2 plus all the way down from oxidation state plus 5 all the way down to vanadium 2. Other reducing agents might not be quite as potent, and it might be that they can only take vanadium 5 down to vanadium 4 or only down to vanadium 3. And that's where the electrode potentials come in. Now, conveniently for us, the example that we've been asked to work with on this course is vanadium species plus zinc. And when we look at the electrode potentials here, we can probably see, now it says predict the outcome. If you want to do it for yourself, pause and go, and then keep listening once you've done it. But I'm going to go straight into it. When I look at the E value for this zinc 2 zinc electrode here, it's the most negative value on the table, which means that this equation contains the best reducing agent on the table. And so out of these reducing agents, VO2 plus, V3 plus, and V2 plus, all written on the right hand side, zinc's the better reducing agent. So what that means is that if I put zinc in with anything from the left hand side of the arrow, VO2 plus, VO2 plus, or V3 plus, then zinc would reduce them. So let's keep clicking through this. Let's write an equation for the first reaction. That's the one between zinc turning into zinc 2 and vanadium 5 turning down into vanadium 4. So I want you to write that equation for yourself and then quickly check it against what comes up on the screen in a moment. So here's the equation then. And what observations would be made? So we can probably look at the picture and quickly work that out. Oh, and then could any further reactions happen? Sorry, I'm clearly not remembering what I put on these slides. So pause the video then, answer those questions, and then come back to me when you're ready to listen on. Well, here we go. So again, like I said earlier, when we look at that table there, zinc's the best reducing agent on the board, which means it can reduce anything you give it from the left-hand side of the arrows, apart from zinc to it, because then it's reacting with itself. That doesn't make sense. The way we'd phrase that, as we did when we looked at E cell, is to say that this electrode potential is greater than or more positive than this electrode potential, and the one that's greater than actually goes as a reduction. It's got a bigger potential to actually go as a reduction. The one with the smaller or more negative E value is going to go backwards, meaning it's going to act as a reducing agent. So there's the combined equation. Okay, E cell's positive, which is reassuring because it would be for the spontaneous reaction. That's the Boa plus the BRA coming together there. We've got 2 electrons in the zinc, only 1 electron in the vanadium 5 to 4 half equation. So there was a bit of doubling that had to be done for the vanadium half equation. Looking at that now, yeah, it looks all good to me. So we've got vanadium 5 going down to vanadium 4 in the presence of H plus with zinc, and there are the products. So what would that look like? Well, we've got a yellow species turning into a blue species. So clearly then it would start yellow and end up blue. But what about in the between? What about when you're sort of halfway there? You've still got some of this yellow vanadium 5 species about, but you're also now have some vanadium 4, which is blue in solution. The colour mixing would occur. It would appear green. So it'd go yellow to blue, and therefore it would go via green. But it's not turning into vanadium 3 plus, which is also green. It's just colour mixing between yellow and blue. So yellow to blue is inevitably going to have a bit of green appear and then disappear as you end up with more of the blue and less of the yellow species. Now, there's going to be another observation. By the way, it must have been that when we do this reaction, and hopefully you'll get a chance to do it for yourselves just to see the colours really, it must be that the solution's acidified. So we're not going to acidify zinc. How would that work? Zinc's a metal. You can't put acid into it. The vanadium species here is an ion, so we'd assume that it's dissolved into water, basically. That would be sensible for us. And so that might be, for example, well, it could be all sorts of things. I'm not going to go into it because I know that what the example I'd give isn't actually what we'd get. It's a bit more complicated. But since that's in solution, it might be that I dissolve my vanadium 5 containing compound into sulfuric acid. So rather than just dissolving it into water, I'll take my vanadium compound, which will be a yellow crystalline solid, and I'll dissolve it into a solution of H2SO4. That means the H plus is present, good to go. That means though that the vanadium species solution is acidic. There is another observation that we'd make. I wonder if you can think what it might be. Well, I'll tell you. As well as the fact that this colour change is happening because of the redox reaction, yellow to blue, which will mean there's a bit of green in between, there would also be another reaction, a side reaction, between the zinc and the H+. Didn't give you the 2H plus 2 electrons makes H2, E value is 0, half equation, didn't give it, but we appreciate that zinc's quite a reactive metal, decent reducing agent, and it can reduce H+, i.e. acid, down to hydrogen. So as well as the colour change we'd expect from the redox, there's actually another redox reaction that would happen at the same time. Some of the other zinc would be reacting with the acidic conditions to make hydrogen, so we'd see effervescence. Fun fact, there you are. Now, that's the first step then. This vanadium 5, this yellow species, based on the E values, can be reduced down to vanadium 4. We've already observed that since zinc is the best reducing agent, it can reduce any of those species. So in other words, once vanadium 5 has been reduced down to vanadium 4, provided that we've still got an abundance of zinc, i.e. it hasn't all been used up, or we haven't run out of H+, because that's also a necessary part of the second reduction, then that VO2+, that's vanadium 4, can be reduced by zinc, by more zinc that hasn't yet reacted, down to vanadium 3. And then that vanadium 3 can go down to vanadium 2, and that's it. Zinc can't reduce vanadium 2 down to vanadium, the metal, so we don't get full displacement of the metal. We don't get solid vanadium out of this. It stops at vanadium 2, which is soluble, so we don't see any precipitates. So let's keep going through this. I want you to practice writing a couple of equations now. So we've said that zinc will further reduce that vanadium species. It's going to go from 5, 4, 3, all the way down to 2. So I want you to write some equations for zinc reducing VO2+ to vanadium 3. Then after that, another set of combined equations for zinc reducing vanadium 3 down to vanadium 2. So you've got two more half equation combinations to do. Shouldn't take you very long, so pause the video, get it done, and then come back to me. Okay, so let's have a look at those. There's vanadium 4 being knocked down to the green species, which is vanadium 3. And then we'd expect that green species to be knocked down even further to violet, which is vanadium 2. So that second one's pretty easy. The first two reductions, vanadium 5 to 4 and then vanadium 4 to 3, both require the presence of H+. So there'd always be an excess of H+. We'd make sure that we just dissolved our original vanadium species into sulfuric acid, and there'd be a large excess of H+, so that wouldn't be a problem. Okie dokie. So there's a bit more we can still say if we were to start combining maybe the vanadium 5, 4, 3, 2 all the way, just combine them into one big half equation. So there they are. Those are our three reductions, zinc reducing vanadium 5 to 4, 4 to 3, 3 to 2. Let's modge those together now. Let's have a half equation for vanadium 5 going all the way down to vanadium 2, and we'll just put it all in one step. The colour change that we'd see as this reaction proceeded would go through those oxidation states though. So it's not just going to go straight from yellow to violet, it is going to go yellow to blue to green to violet. And actually, by convenience, this colour gradient I've used here, you can see that there's yellow to blue, and in between there's a bit of yellow and blue. So we would see a greenish solution, but it's not vanadium 3 at that point. We're halfway between 5 and 4. Then we go from vanadium 4, the reaction continues, and the solution overall appears more green, bluey green at first, and then green. And then finally we go through this transition from vanadium 3 to vanadium 2. The zinc just keeps going until it runs out, or the vanadium runs out, and then we've got green turning to violet. And you do see that nice colour change as it progresses. So let's combine those half equations then. Let's take the vanadium species. So have a close look at that half equation there. Vanadium 5, I've shown it going straight down to vanadium 2, which would go through this transition. It's three half equations combined to make one half equation that we then combine with the zinc to make one overall equation. It's the same effect of just combining all of those three equations from the top. That's the same effect. So what we get is, well, first of all, there's a bit of electron accounting to do, so triple the one and double the other, so that we have 6 electrons represented in both half equations. Then we can combine them. So we get 3 zincs makes 3 zinc 2s, and then 2 of the vanadium half equation. And you'll see that that is just this put together. If you combined all three of these equations and then cancelled out everything that repeats, so as a reactant and a product, so that's a reactant because it's a product there, so they'll cancel. That's what you get. So, in summary, we've practiced some half equations there. You need to know the colours of these: yellow, blue, green, violet for 5432 for vanadium. You'll be able to work with electrode potentials if you need to, as per what we've covered in each cell. And don't forget, at the beginning, we also had a look at how pH and ligands also affect the electrode potential for a given ion. So if I just flick through to the last slide. Oh, I forgot about this bit. This is the last bit now. So there's another example that we're going to look at. So as well as the other bits that we've seen, there's yet another reminder about the silver mirror test. We did it in organic. We saw it in the complexes lesson as well. Just a little bit more detail here. There's very little we could say that we haven't already said. Tollens reagent is sometimes also referred to as ammoniacal silver nitrate. Ammoniacal is this silver complex, silver bisamine 1. So that's two ammonia ligands forming a coordinate bond through the lone pair on the end of the silver, being reduced. Now, yeah, it's silver nitrate. There's clearly no nitrate in this equation. The nitrate is a spectator ion, so it's balancing the charge on that. It's soluble. The way that you make ammoniacal silver nitrate, i.e. Tollens reagent, is we normally just make it just before you're ready to use it. You take a silver nitrate solution and you add concentrated ammonia. And that shifts off some of the aqua ligands that we'd expect to be in an aqueous on the silver, in an aqueous solution of silver nitrate. So in aqueous silver nitrate, again, the nitrate's a spectator, which is why it doesn't appear here. We'd expect two waters. You have conc ammonia, which means the solution is going to be quite alkaline, and it displaces the water ligands, and you get ammonia ligands attached. In the silver mirror test, that silver amine ligand complex gets reduced down to elemental silver, which is what the mirror is. The ligands get booted off because this isn't a positive metal ion anymore. It's not attractive to those ligands anymore. Those coordinate bonds aren't going to hold. And so the ligands get displaced and contribute to the alkalinity of the solution, because ammonia is a weak base, don't forget. It can react with H2O to make NH4 plus and OH minus. Something else must be getting oxidized then. If the silver gets reduced from silver 1 to silver, then something must be getting oxidized. And that something is, of course, an aldehyde, because this is the test for an aldehyde. So it doesn't matter what the aldehyde is. There's a simplified example of a structure, so just like using R there as a placeholder, and the carboxylic acid. Another complication, this would be alkaline conditions, because we've got ammonia present. And practically, as I said, when you make ammoniacal silver nitrate, you're putting ammonia solution, you're making an ammonia solution basically, so it becomes more alkaline. So we'd expect the COH carboxylic acid more oxidized functional group that forms to come off in the form of a carboxylate rather than a carboxylic acid. We can balance that half equation, but it's quite a challenge and it involves using hydroxide. We're not allowed to use H plus here because we'd expect this to be alkaline conditions. So if you want to have a go at that, do. If you're happy to sit back and continue to watch, then you can do that instead. I need to put an O atom in. Clearly this equation isn't balanced. I can't use H plus. I can use H2O and OH minus if I need to. So I'll put an OH and OH minus in there. I could have tried a H2O, might have found it works, but I might have been stuck with the need to make a H plus, and H plus wouldn't be forming here, it would form as water because there's hydroxide around as well. Then to balance it, I'm going to think, well, there's going to be some hydrogen to account for. H plus isn't an option because we're talking alkaline conditions, so any H plus that would have been formed, i.e. any H's that drop off, are going to come off in the form of H2O. Then that needs balancing some more. I'm going to do the electrons last by balancing charge. So what do we have? On the left, we've got, well, 2 O's and 2 H's. On the right, we've got 3 O's and 2 H's. A little bit awkward. Might be a bit of trial and error at this point, but if I pop a 3 on there. Now, the reason I popped a 3 on there is because I need more H. I need an even number of H at that. And if I add just one hydroxide, which is what I had, it doesn't balance. So the next option really is add 3 hydroxides, because with that H in the aldehyde, I've got an even number, so I can have it works with the H2O on the other side, because obviously there are 2 H's in H2O. Then I look at that a bit more, I say, okay, well, I'm getting there. Now I've got 4 H's on both sides by putting the 2 in front of the H2O. It's just balancing equations, but now that's balanced in terms of atoms. Charge, 3 negative charges on the left-hand side, so it must be 2, watch out here, electrons on the right. Why 2? Well, because there's a negative charge just there. If that came off as RCOOH, then we'd have one H2O, two O hydroxides. It'd still be two electrons because that's the redox bit. So that suddenly seems a lot more complicated than just saying it's used in the silver mirror test, but that's everything we could say. I don't expect, but the reason I've gone through it is because it could well. I don't expect that any organic half equations, we have seen them in the past, but they're quite rare, are going to pop up on any assessments or exams, but it's best safe than sorry. So there we are. Be aware of the silver mirror test. Be aware that it's that species. That's really all that we have to say for the course. To review the specification then, there's one bit of this section we haven't done. That comes next lesson. You can see the list there. Make sure you know those vanadium colours. Obviously, we appreciate that there are variable oxidation states. That's basically the thing that underpins this whole topic. This statement here about pH and ligand is a little bit elusive, and there aren't many good quality notes or videos to explain that out there, but hopefully I've covered it in a way that's helped you see that it's a thing by looking at some specific examples. Where we go next then is redox titrations. So that's next lesson's work, and there'll be quite a lot of calculation practice coming off the back of that. So that's it for now. Thank you very much.